So this is part 2, number 3 and number 5. Is that correct?
Yes.
The problems on matrices or the problems on permutations?
On permutations.
Okay. So we have the permutation alpha, which is 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. And the permutation sigma, which is 1 goes to 3, 2 goes to 4, 3 goes to 1, and 4 goes to 2. And we want to calculate tau, which is alpha sigma alpha inverse. So, of course, we have to know what is alpha inverse. So if alpha sends 4 to 1, alpha inverse sends 1 back to 4. Alpha sends 1 to 2, so the inverse sends 2 to 1. Alpha sends 2 to 3, so the inverse sends 3 back to 2. And alpha sends 3 to 4, so the inverse sends 4 to 3. So tau is the product of these 3 permutations: 1, 2, 3, 4, 2, 3, 4, 1. 1, 2, 3, 4, 3, 4, 1, 2. And 1, 2, 3, 4, 4, 1, 2, 3. So this is one way to do it. So this is the product of the 3 permutations written in standard form. And what happens to 1? When you multiply these permutations, 1 goes to 4, 4 to 2, 2 to 3. So and 1 ends up at 3. Right? Does that make sense? Is that clear? Because that's the basic step.
Yes.
1 goes to 4, then 4 to 2, then 2 to 3. So 1 ends up at 3. 2 goes to 1, then to 3, then 3 to 4. 3 goes to 2, 2 goes to 4, 4 goes to 1. 4 goes to 3, 3 is sent to 1, 1 is sent to 2. So this is the permutation that you end up with. Now, if you wanted to write these as products of cycles, alpha as a cycle, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1. So alpha is a 4 cycle. And sigma, 1 goes to 3, 3 goes back to 1. That's a transposition. Then 2 goes to 4, and 4 goes back to 2. So this is a product of two cycles or transpositions. So tau, which is alpha sigma alpha inverse. So this is also alpha. What is sigma? Sigma is 1, 3, 2, 4. Alpha inverse. Let's see. Let me just double check that I didn't do anything wrong. So alpha, alpha is 1, 2, 3, 4. And sigma is 1, 3, 2, 4. So alpha sigma alpha inverse, 1, 2, 3, 4, 2, 3, 4, 1. This is my sigma, and this is alpha inverse. So 1 to 4 to 2 to 3, 1 goes to 3, 2 goes to 1, goes to 3, goes to 4. Yeah, that's fine. So if I took, I mean, this is correct, but maybe all I wanted to do was to write tau also as a product of transpositions. 1 goes to 3, goes back to 1. 2 goes to 4, goes back to 2. So it turns out in this case that alpha, sigma, alpha inverse, which is tau, but 1, 3, 2, 4, that's just sigma. That's just sigma. So that's what it turns out to be. In any case, I wrote writing sigma as a product of disjoint cycles and tau as a product of disjoint cycles. Turns out they're the same permutation. That's just what happens in this instance. Okay. Are there any questions about that? Okay, and what was the other problem you asked about?
Number 5.
Okay. So part 2, number 5. We have the permutation sigma in S5. In the standard form, this is what it is, 2, 3, 1, 5, 4. If you write it as a product of cycles, 1 goes to 2, 2 goes to 3, 3 goes back to 1, 4 goes to 5, and 5 goes back to 4. So sigma is the product of a 3-cycle and a 2-cycle. And tau is 3, 4, 5, 2, 1. So 1 goes to 3, goes to 5, goes back to 1, and 2 goes to 4, and 4 goes to 2. So sigma and tau are both products of a 3-cycle and a 2-cycle. Alpha, so that's part A. Part B, alpha is the permutation 1, 2, 3, 4, 5, goes to 1, 3, 5, 2, 4, and beta is the permutation 5, 1, 3, 2, 4. And we want to prove that alpha sigma alpha inverse turns out to be the same permutation as beta sigma beta inverse. Right? You know, quote a tau, but this is what you want to prove. So one way to do it is just to actually do the calculation. So alpha sigma alpha inverse is 1, 2, 3, 4, 5, 1, 3, 5, 2, 4 times sigma 2, 3, 1, 5, 4 times alpha inverse. So here's alpha. What is the inverse? 1 goes to 1, 2 goes to 4 in the inverse, 3 goes to 2, 4 goes to 5, 5 goes to 3. And then you make the calculation. 1 goes to 1, goes to 2, to 3. 2 goes to 4, 4 to 5, 5 to 4. 3 to 2, 2 to 3, 3 to 5. 4 to 5, 5 to 4, 4 to 2. 5 to 3, 3 to 1, 1 to 1. So this is tau. Now, notice that sigma, this is sigma as a product of disjoint cycles. What is alpha as a product of disjoint cycles? 1 goes to 1, that's just a fixed point. 2 goes to 3, 3 goes to 5, 5 goes to 4, 4 goes back to 2. So that's alpha. And alpha sigma alpha inverse, if we were to write this as a product of cycles, it's 1 goes to 3, goes to 5, goes back to 1, and 2 goes to 4, goes to 2. So this is alpha sigma alpha inverse. Now, there's a theorem that is proved, it's in the notes certainly, that says if you have alpha times some permutation, some cycle, times alpha inverse, this is a K cycle, you get another K cycle, and alpha of B1 gets sent to alpha of B2 and so forth up to alpha of B sub K. So this is a fact about multiplying a cycle by a permutation on the left and its inverse on the right. So if we have alpha, here's my sigma, 1, 3, 5, 2, 4, alpha inverse. This would be, the 3 cycle becomes alpha 1, alpha 3, alpha 5, and the 2 cycle is alpha 2, alpha 4. What is alpha 1, alpha 3, alpha 5? Well, here's alpha. Alpha of 1 is 1. Alpha of 3 is 5. Alpha of 5 is 4. And see what happened to my sigma? Into this. Oh, and alpha of 2, alpha of 4. Alpha of 2 is 3, and alpha of 4 is 2. Let's see. Alpha of 5 is alpha of 2 is 3. Oh, alpha of 4 is 2. So let me just double check this calculation because there's one part of it I don't like. So here is a fact that I'm using, which says if you have a cycle, B1, B2 up to B sub K, so this is a K cycle, and you take a permutation alpha and multiply it by alpha inverse, what does this do? Well, if you apply this to alpha of B sub I, alpha inverse of alpha of BI is BI. BI goes to BI plus 1, and that goes to alpha of BI plus 1. So what you get is a cycle, alpha of B1, alpha of B2, up to alpha of B sub K. So if you take a cycle and you multiply it by alpha on the left and alpha inverse on the right, you just change the numbers in the cycle. So for example, when alpha in this problem is the permutation 2, 3, 5, 4, and sigma is the permutation 1, 2, 3, 4, 5, then alpha, sigma, alpha inverse, 1, 2, 3, this will be alpha of 1, alpha of 2, alpha of 3, and the cycle alpha 4, alpha 5. So alpha of 1 is 1, alpha of 2 is 3, alpha of 3 is 5, and alpha of 4 is 5, and alpha of 5 is 4. Oops. Sorry, alpha of 4 is 2, and alpha of 5 is 4. So yeah, and that's exactly what I got when I did the calculation just by multiplying the 3 permutations together and getting the result. I mean, it's just like with any other kind of arithmetic problem, there are lots of ways to do it, but in any case, there's only one answer. Any questions about that? And computing beta sigma beta inverse is just another calculation of the same sort.
Can you go over question 14 in part 1?
So part 1, number 14, we want to use the Chinese remainder theorem. First of all, the first is x congruent to 2 mod 5 and x congruent to 3 mod 7. And the Chinese remainder theorem says that a solution exists if 3 minus 2 is congruent to 0 modulo the greatest common divisor of the moduli 5 and 7. That means 1 congruent to 0 mod 1, or 1 divides 1, which is certainly true. So we know from the Chinese remainder theorem there is a solution, and all we have to do is calculate it. So if x is congruent to 2 mod 5, that means x is a number of the form 2 plus 5y. That's what it means to be congruent to 2 mod 5. And if x is also congruent to 3 mod 7, that means 2 plus 5y is congruent to 3 mod 7, which means 5y is congruent to 1 mod 7. So you need to find the solution to that congruence. Can someone tell me a solution? What is the solution to this linear congruence?
Three.
So if y is congruent to 3 mod 7, then 5y is congruent to 5 times 3, which is 15, which is 1 mod 7. So y congruent to 3 mod 7 is a solution. So any solution will be y equal to 3 plus 7 times some number z. And if x is 2 plus 5y, that's 2 plus 5 times a number of the form 3 plus 7z, which is 2 plus 15 plus 35z, which is 17 plus 35z. So 17 is a solution because 17 minus 2 is 15 is divisible by 5, and 17 minus 3 is 14 is divisible by 7, and every solution is congruent to 17 mod 35. So the solution is a whole congruence class, all x congruent to 17 mod 35.
Why it's mod 35?
Well, 2 reasons. First, so let's just go, because the proof, first of all, tells us that if x is 2 mod 5, then x is 2 plus 5y for any y, okay?
Mm-hmm.
And then, but that's also congruent to 3 mod 7. So x is of the form 2 plus 5y, and y is a solution of this congruence, which is the same as 5y congruent to 1 mod 7, which is the same as y congruent to 3 mod 7. So the solutions of this congruence are all numbers of the form 3 plus 7z. And so x, which is 2 plus 5y, is any number of this form, which is any number 17 plus 35z. So for any z, so the set of all numbers of the form 17 plus 35z, that's the definition of the congruence class. That is all x which are congruent to 17 modulo 35.
Okay, got it. Thank you.
So it's important to remember the Chinese remainder theorem. It says if you have a pair of congruents, x is x congruent to A mod M and x congruent to B mod N. So this pair of congruents has a solution if and only if A is congruent to B modulo the greatest common divisor of M and N. And if this holds, then if x is a solution, I say x naught is a solution, then x is also a solution if and only if x is congruent to x naught modulo the least common multiple of M and N. So in that previous problem, the first modulus was 5, the other modulus was 7, the GCD of 5 and 7 is 1, so there's a solution, and the least common multiple of 5 and 7 is 35. So the solution consists of exactly one congruence class mod 35. Now let's see, in number 14, part B, we have x congruent to 2 mod 15, x congruent to 3 mod 21. So we look at the condition for a solution. Is 2 congruent to 3 modulo the GCD of 15 and 21? Well, the greatest common divisor of 15 and 21 is 3, and 2 is not congruent to 3 mod 3 mod 3. 3 doesn't divide 1, therefore no solution. All right. Any questions about this? The Chinese remainder theorem is one of the basic facts about congruences. Other questions? Let's see, someone's asking question 12 from part 1. So part 1, number 12, we have the Euler phi function. Phi of m, which is the number of integers k from 0 to m minus 1, or you could say from 1 to m, where the greatest common divisor of k and m is 1. So for phi of 2, you look at the numbers 0 and 1. And let's cross out the numbers that are not relatively prime to 2. Well, 0 is divisible by 2, so it's not relatively prime to 2. So we cross out 0, and there's just 1 left. So phi of 2 is equal to 1. What about phi of 3? We look at the numbers 0, 1, and 2. Which of these are divisible by 3? Just 1 and 2. So phi of 3 is 2. What is phi of 4? You look at the numbers 0, 1, 2, and 3, and which have a factor in common with 4? Well, 0 and 2 are both divisible by 2, so they have a common factor with 4, and that just leaves 1 and 3, so phi of 4 is 2. What about phi of 5? So you look at the numbers from 0 up to 5 minus 1 or 4. You have a factor in common with 5 only if it's divisible by 5, because 5 is a prime. 5 divides 0, but 5 does not divide 1, 2, 3, or 4. So phi of 5 is 4. What about phi of 6? You look at the numbers 1, 2, 3, 4, 5. Which of these numbers have a factor in common with 6? That means divisible by 2 or 3. Well, 0, 2, and 4 are divisible by 2, and 3 is divisible by 3. There are only 2 numbers left, 1 and 5. So phi of 6 is equal to 2. You know, let me just do a few more quickly. 7, 0, 1, 2, 3, 4, 5, 6. Well, a number divides 7 only if it's 1 or 7. So the numbers divisible by 7 are just 0, and that leaves 6 left. So phi of 7 is equal to 6. What about phi of 8? You look at the numbers from 0 to 7. The numbers that have a factor in common with 8 are the even numbers, 0, 2, 4, and 6. And that leaves 4 numbers. So phi of 8 is 4, and so on. I mean, it just continues in that way. Actually, I can do them all. Phi of 9 and phi of 10. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 8. You have a factor in common with 9 only if you're divisible by 3. That's 0, 3, and 6. The other 6 numbers have no factor in common with 9, so phi of 9 is 6. And phi of 10, you take the numbers from 0 to 10, and every even number is divisible by 2, and 2 divides 10, so you cross off the even numbers. The only other number that has a factor in common with 10 is a number divisible by 5. That's just 5. So you're left with 1, 3, 7, and 9. So phi of 10 is equal to 4. So that's it.
Can you go over question 13 in part 1?
So part 1, number 13. This is just solving some linear congruences. So 9x congruent to 15 mod 21. Remember the theorem, ax congruent to b mod m has a solution if and only if this b is congruent to 0 modulo the greatest common divisor of a and m. So you check, is 15 congruent to 0 modulo the greatest common divisor of 9 and 21? Well, the greatest common divisor of 9 and 21 is 3, and 15 is congruent to 0 mod 3. So that condition is satisfied. And so this is going to have a solution. If you have an ax congruent to b mod m, and d is a number that divides a, b, and m, so ax congruent to b mod m, what does that mean? It means that ax is b plus my for some y. If you divide this congruence by d, because d divides am and a, b, and m, a over d times x, that's an integer, b over equals b over d plus m over d times y. That means that a over d times x is congruent to b over d modulo m over d. So when you have a congruence and a number that divides this, this, and this, you can divide by it. So from 9x congruent to 5 mod 21, we can say that 9 over 3x, sorry, this is 15, is congruent to 15 over 3 mod 21 over 3. So 3x is congruent to 5 modulo 7. So any solution of the first congruence will be a solution of the second, and conversely. So we just have to find solutions of this. And you can do it, for example, by trial and error. When x is 0, you get 0 congruent to 5, no. When x is 1, 3 congruent to 5, no. When x is 2, 6 congruent to 5, mod 7, no. When x is 3, 9 congruent to 5, no. When x is 4, 12 congruent to 5, yes. So if x is congruent to 4, mod 7, 3x is congruent to 12, that is congruent to 4 mod 7. So the solution of the original congruence is anything congruent to 4 mod 7. And yeah. Or if you want the congruence is mod 21, to say x is congruent to 4 mod 7 is the same as saying x is congruent to 4 mod 21, or x is congruent to 11 mod 21, or x is congruent to, just keep adding 7, 18 mod 21. So there are 3 congruence classes mod 21, which are the solutions of the original congruence, or 1 congruence class mod 7. Are there any questions about this? These are, things that, these are just calculations that you have to know how to do. Let me do the other 2 parts. So 14b, 8x congruent to 15 mod 26. So the JCD of 8 and 26 is 2. And 15 is not congruent to 0 mod 2. So there's no solution. So find all integer solutions. Well, the answer is there are none for this congruence because it doesn't satisfy the necessary and sufficient condition for a linear congruence to be solvable. Let's see, part C, 14x congruent to 21 mod 17. So the GCD of A and M, that's the GCD of 14 and 17 is 1. So this will have a solution. And I don't know, it's how to find it is a little bit hard. So solve the congruence. So one way to do it is just trial and error. Start trying all the different values of x until you get a solution. That's one method. I mean, that just takes some work. Sometimes you have to do some work. Another way is to use the Euclidean algorithm. So the GCD of 14 and 17 is 1. So we know that from the Euclidean algorithm, we can find a way to write 1 as 14 times, I'll call it x naught, plus 17 y naught. So once you have x naught and y naught, 21 is 14 times x naught times 21 plus 17 times y naught times 21. So 14 times 21 x naught will be congruent to 21 mod 17. So let me work this out just so you can see what I mean. Let's apply the Euclidean algorithm to 17 and 14. So 17 is 14 times 1 plus 3. 14 is 3 times 4 plus 2. 4 is 3 times 1. Sorry. 17 is 14 times 1 plus 3. 14 is 3 times 4 times 2. 3 is 2 times 1 plus 1. So 1 is 3 minus 2. 2 is 14 minus 3 times 4. So this is 3 minus 3 times 4. That's 5 times 3 minus 1 times 14. And 3 is 17 minus 14 minus 14. So this is 5 times 17 minus 6 times 14. So we have our nice equation. Let's see. 1 equals, let me write this, minus 6 times 14 plus 5 times 17. So 21 is minus 6 times 21 times 14 plus 5 times 21 times 17. In other words, 21 is congruent to minus 126 times 14 mod 17. So one solution of the congruence is x equals minus 126, or anything congruent to minus 126 mod 17. What's the least non-negative residue of 120 of minus 126 mod 17? I don't know. If you divide 17 into 126, that goes 7 times minus. So I think that x is congruent to 10 mod 17 because minus 126, 136 divided by 17. Is that right? Yeah. So a smallest non-negative solution is x anything congruent to 10 mod 17. Let's just check. 14 times 10 is 140. 140 minus 21 is 119. Is 119 divisible by 7? So I think that if you take, so divisible by 17, 7 times 17 is 119. So that's a solution. And it seems that no matter how you do it, it still is going to take some work, but sometimes you have to work. Right. Any questions about this? So part 1, number 6. So you want to find a complete set of residues mod 9. Modulo 9, which are all odd. So what are the congruence classes mod 9? 0, 1, 2, 3, 4, 5, 6, 7, and 8. Now, of course, 1 is odd, so 1 is congruent to 1, 3 congruent to 3, 5 congruent to 5, 7 congruent to 7. So these 5 congruence classes are odd. What's an odd number congruent to 0 mod 9? Well, 9. What's an odd number congruent to 2 mod 9? Well, 11 is. 11 is 2 mod 9. I mean, there are many others. I mean, 101 would also be an odd number congruent to 2 mod 9. 13 is congruent to 4 mod 9. 15 is congruent to 6 mod 9. 17 is congruent to 8 mod 9. So here we have a complete set of residues modulo 9, and every number in that set is an odd integer. So that's what we were asked to do. What was the other question you asked about? Number 8? Yeah, that's number 8. Oh, question 6 also. Okay, so number 6, that's a nice question. So this was number 8. Number 6 was prove that if a number 2 to the n minus 1 is prime, then the exponent n is prime. And there's a hint. It says, consider the factorization of x to the n minus 1. So you know you can factor this, for example, as x minus 1 times 1 plus x squared up to x to the n minus 1. And if you had, for example, n was like d times k, then x to the n minus 1, that's x to the d times k minus 1. That would be like x to the d raised to the kth power minus 1, right? Because n is dk. And then this would factor as x to the d minus 1 times 1 plus x to the d plus x to the 2d up to just replacing x by x to the d and n by k minus 1. We have a factorization like this. So if n is a composite number, so d and k are both strictly less than n and strictly bigger than 1, then 2 to the n minus 1 would be, I'm just plugging in x equal 2 to the d minus 1 times 1 plus 2 to the d plus 2 to the 4d up to 2 to the k minus 1 times d. And this is a factorization. Because 2 to the d minus 1 is bigger than 1 and less than this, so it's not prime. So if you have a number 2 to the n minus 1 and n is composite, then 2 to the n minus 1 is not a prime. So the converse is that if this is a prime, then n has to be a prime number. That's the chain of reasoning there. I mean, that's one way to do it. It just reduces the problem to high school algebra factorization. Anything else? Okay, so again, that's it.